Implementation in dominant strategies. In this section, our aim is to put the issue of incentive compatibility in a wider context. The mechanisms considered so far extract information from the different players by motivating them to tell the truth. More generally, one may think of other indirect methods of extracting sufficient information from the participants. Perhaps one may devise some complex protocol that achieves the required social choice when players act strategically. This section will formalize these more general mechanisms and the associated notions describing what happens when players act strategically. Deviating from the common treatment in economics, in this section we will describe a model that does not involve any distributional assumptions. Many of the classical results of mechanism design are captured in this framework, including most of the existing applications in computational settings. In section 9.6, we will add this ingredient of distributional assumptions reaching the general Bayesian models. Games with strict incomplete information. How do we model strategic behavior of the players when they are missing some of the information that specifies the game? Specifically, in our setting, a player does not know the private information of the other players, information that determines their preferences. The standard setting in game theory supposes, on the other hand, that the rules of the game, including the utilities of all players, are public knowledge. We will use a model of games with independent private values and strict incomplete information. Let us explain the terms. Independent private values means that the utility of a player depends fully on his private information and not on any information of others, as it is independent from his own information. Strict incomplete information is a not completely standard term. That means that we will have no probabilistic information in the model. An alternative term sometimes used is pre-Bayesian. From a CS perspective, it means that we will use a worst-case analysis over unknown information. So here is the model. Definition 9.21. A game with the independent private values and strict incomplete information for a set of n players is given by the following ingredients. 1. For every player I, a set of actions xi. 2. For every player I, a set of types ti. A value little ti in capital Ti is the private information that I has. 3. For every player I, a utility function ui, which is defined from the domain of Ti multiplied by x1 multiplied by x2 and so on, multiplied by xn, the product of all of these terms, and the range is in R, where ui of Ti x1, x2, x3 until xn is the utility achieved by player I if his type private information is Ti, and the profile of actions taken by all players is x1, x2, x3 until xn. The main idea that we wish to capture with this definition is that each player I must choose his action xi when knowing Ti but not the other Tj's. Note that the Tj's do not affect his utility, but they do affect how the other players behave. Thus, the interplay between the different xi's is more delicate than in regular games. The total behavior of player I in such a setting is captured by a function that specifies which action xi is taken for every possible type Ti. This is termed a strategy. It is these strategies that we want to be in equilibrium. Definition 9.22. A strategy of player I is a function Si which maps from Ti to Xi. A profile of strategies S1, S2, S3, and to Sn is an ex post Nash equilibrium if for every T1, T2, T3, until Tn, we have that the actions S1 of T1, S2 of T2, and so on until Sn of Tn are in Nash equilibrium in the full information game defined by the Ti's. Formally, for all I, O, T1, T2, T3 until Tn and O xi prime, we have that ui of Ti, Si of Ti, S minus I of T minus I is greater than or equals to ui of Ti xi prime and S minus I of T minus I. The strategy Si is a weakly dominant strategy. If for every Ti we have that the action Si of Ti is the dominant strategy in the full information game defined by Ti. Formally, for all Ti or x minus I and O xi prime, we have that ui of Ti, Si of Ti, x minus I is greater than or equals to ui of Ti xi prime x minus I. The profile S1, S2, S3 until Sn is called a dominant strategy equilibrium if each Si is a dominant strategy. Thus, the notion of X post Nash requires that Si of Ti is a best response to Si of T minus I for every possible value of T minus I, i.e. without knowing any about T minus I, but rather only knowing the forms of the other players' strategies as minus I as functions. The notion of dominant strategy requires that Si of Ti is the best response to any x minus I possible, i.e. without knowing anything about T minus I or about S minus I. Both of these definitions seem too good to be true. How likely is it that a player has a single action that is the best response to O x minus I or even to O S minus I of T minus I? Indeed, in usual cases, one does not expect games with the strict incomplete information to have any of these equilibria. However, in the context of a mechanism design, where we get to design the game, we can sometimes make sure that they do exist. While at first sight the notion of dominant strategy equilibrium seems much stronger than ex post Nash, this is only due to actions that are never used. Proposition 9.23. Let S1, S2, S3 until Sn be an ex post Nash equilibrium of a game. Xi, x1, x2, x3 until xn, t1, t2, t3 until tn, u1, u2, u3 until un. Define xi prime equals to the set of si of ti such that si of little ti such that little ti is in capital Ti. And i.e. xi prime is the actual range of Si in Xi. Then S1, S2, S3 until Sn is the dominant strategy equilibrium in the game. X1 prime, X2 prime, and so on until Xn prime, T1, T2, T3 until Tn, U1, U2, U3 until Un. Proof that Xi equals to Si of Ti, which is in capital Xi prime, and the little xi prime is in capital Xi prime. And for every j not equals to I little s, xj is in capital Xj prime. By definition of capital Xj prime, for every j not equals to I, there exists the little tj prime, which is in capital Tj, such that Sj of Tj equals to Xj. Since S1, S2, S3 until Sn is an X post Nash equilibrium, Ui of Ti, Si of Ti, S minus I of T minus I, the utility is greater than or equals to Ui of Ti xi prime S minus I of T minus I. And as x minus I equals to S minus I of T minus I, we get actually Ui of Ti Si of Ti x minus I is greater than or equals to Ui of Ti xi prime x minus I as required in the definition of dominant strategies.